Hi everyone, welcome to our lecture on necessity and sufficiency. Today we're going to go over the definitions of these important logical properties and we'll prove some things about them. So this is going to be a very exciting lecture. Necessity and sufficiency are really important logical properties, and it's absolutely imperative that you know what they mean and are really comfortable using them after taking a logic class. Okay, so let's get started. Okay, so let's start with the definition of a sufficient condition. A property F is a sufficient condition for a property G if and only if, whenever F is present, G is present. Okay, so try to think about what that means and really internalize this definition. So what it means is that the occurrence of F guarantees the occurrence of G. Can you think of any examples? Here's one. Eating too much is a sufficient condition for having a stomach ache, right? Stomach aches can have many different causes. It can be a bacteria, it can be from drinking milk, it can be from eating too much. But eating too much is a sufficient cause. If you eat way too much, you're basically guaranteed to have a stomach ache. Here's another example. Knowing I'm in Irvine is sufficient to know that I'm in California. If you know that I'm in Irvine, then you already are guaranteed that I'm going to be in California, right? Because Irvine is in California. So Irvine is a more specific property of where I'm at than California, right? Because if I tell you if I'm in California, it could be in San Francisco, Los Angeles, Northern California, etc. Let's look at an example from last time. Being a bank teller and a feminist is sufficient for being a bank teller. Right? If I know that Linda is both a bank teller and a feminist, then I'm guaranteed to know that she's going to be a bank teller. And so sufficient conditions, generally the property F here is going to be more specific. It's going to be a stronger property than the property G. Great. Let's move on now to necessary conditions and look at a definition. You always start with the definitions. So property A is a necessary condition for property B if and only if, whenever B is present, A is present. So you see that this is a sort of opposite of a sufficient condition. So in other words, the occurrence of B guarantees the occurrence of A. Remember that if A is a sufficient condition for B, then the occurrence of A guarantees the occurrence of B. But here, if A is a necessary condition for B, then the occurrence of B guarantees the occurrence of A. Pause the video now and try to come up with an example. Here's one. Having four sides is a necessary but not sufficient condition for being a square. Why is it not a sufficient condition for being a square? Well, because there's other geometrical shapes that have four sides. For example, a rectangle that is not a square. And here's another example, going back to the Linda example that we had. Being a bank teller is necessary for being a bank teller and a feminist, right? So the necessary condition is also in a way weaker. It encompasses more things. Okay, we've seen the definitions in some examples. Let's try to still make sure that we fully understand these definitions. Okay, A is a sufficient condition for B means that if A is present, then B is present. That just comes from the definition. But I do like to look at things visually. So here's a little diagram. Suppose that we have a circle A like this. You can imagine it to be California, you can imagine it to be a neighborhood, imagine it to be anything. A encompasses all the red things here. Now, suppose I also tell you that the square B is put on top of A, such that, for example, you can imagine that B is like Irvine. So Irvine is still in California, but not all of California is Irvine. Okay, now ask yourself, is A sufficient for B? So what does that mean? Does it mean that, is it true that whenever A is present, then B is present? let's look at here where the arrow is pointing at. In the regions where A is red here, then there B is not present. So it's not the case that if A is present, then B is present. There are many cases where A is present, but B is not present. But now you can ask, is B sufficient for A? Is knowing B sufficient for knowing A? And in this case, the answer is yes. Look at the arrow pointing at B, right? If I know that I'm in Irvine, I always know that I'm in California. There's no exceptions. So in this case, B is a sufficient property for A, or sufficient condition for property A. Okay, so we got an intuitive and diagrammatic feel for what it means for a property to be a sufficient condition of another property. Now let's look at necessary conditions. And it helps to look at thinking about, well, what does it mean for something not to be a necessary condition for another property? Okay, so B is not a necessary condition for A. What that means is that there's a case where A is present, but B is not present, right? Because if B is a necessary condition for A, then that means that whenever A is present, then B is also necessarily present. But if it's not a necessary condition, then it means that there's at least one case where A is present, but B is not. Again, let's look at this with our diagrams. So here's A again, and we put B just as before. Now ask yourself, is A necessary for B? I understand that these with A's, B's, F's, G's can get a little bit confusing, but eventually you'll get the hang of it. Okay, so when trying to ask, is A necessary for B, it's important to think about, well, is it possible for A not to be necessary for B? What would it mean for A not to be necessary for B? Well, it means that there's a case where B is present and A is not present. Is there such a case? No, there's not, right? Because every time that B is present, then A is present. So, what does that mean? Is A necessary for B? Yes, it is. There's no case where A is present, but B is not. Okay, so let's try switching these around. Is B necessary for A? So again, ask yourself, is it possible for B not to be necessary for A? And what would that mean? That would mean, is there a case where A is present, but B is not? Well, of course there is. The whole part of A that's red but not blue is going to be such a case. So is B necessary for A? No, it's not. And here's just one example of where that's the case, right? Where the arrow is pointing, A is present, but B is not. So there's no case where B is present, but A is not. Think of this as the California example. Is it the case that being in Irvine is necessary for being in California? Well, then ask yourself, is it possible to be in California but not be in Irvine? Well, of course it is. You can be in Los Angeles or in San Francisco. So, being in Irvine is not necessary for being in California. Okay, we've looked at some definitions of necessity and sufficiency, and we've looked at some examples and some intuitive understanding of it through the diagrams. Now we have the tools to actually prove things about these properties. And what we're going to do is prove together that if A is a sufficient condition for B, then B is a necessary condition for A. Right? We're going to prove this in all cases. You might have already noticed that there seemed to be a sort of symmetry between sufficiency and necessity, right? But just having that feeling isn't sufficient for it being true. We need to show it with a proof, and that's what we're going to do. So how do we even begin? So, okay, the statement we want to prove is if A is a sufficient condition for B, then B is a necessary condition for A. So what we want to do is we want to assume that A is actually a sufficient condition for B, because we want to assume, this is called the antecedent, but that's not important. What we want to do is assume this part, that the if takes on, and then show, okay, if this is the case, then this other thing happens. So let's start with that. Proof. Suppose that A is actually a sufficient condition for B. Okay, that's the first thing we do. Now think of using the definitions. What does it mean for A to be a sufficient condition for B? That means that whenever A is present, then B is present. Okay, so we seem kind of stuck here. But to show that B, this second part of the statement, which is called the consequent, to show that B is a necessary condition for A, let's ask ourselves, is it possible for B not to be necessary for A? Right? And is it possible for B not to be necessary for A given the thing that we assumed at the beginning, namely that A is a sufficient condition for B? Okay, so how can we find that out? Well, we do what we've been doing throughout this video and in other ones. We suppose, and this is for contradiction, that B is not necessary for A. Why do we do this? Because we suppose the opposite of what we want to show. And if we say, well, could that be true? And if it's impossible for that to be true, then the original thing must be true. Okay, so let's go on. So suppose for contradiction that B is not a necessary for A. This would mean, right, we always go back to the definitions. What would it mean for B not to be necessary for A? This would mean that there's a case where B is present and A is not present, right? We saw that from before. Now, do you see something weird here? We've assumed that A is sufficient for B, which means that whenever A is present, B is present. But then we've also supposed for contradiction that B is not necessary for A, which means that if B is present, then A is not present. But we just said that whenever A is present, then B is not present. So this is what you call a contradiction. It's not possible for B not to be necessary for A. So what we do is we say, look, let's assume the opposite of what we want to show, and show that assuming the opposite is impossible. And if you show that assuming the opposite is impossible, then it must be true, then the original statement is true. And so we've proved that B is necessary for A. We've proved it for every possible case. That's pretty neat, right? And some of the exercises for your homework are going to be to prove such statements. Okay, so now you know, by proving that in every case, if A is a sufficient condition for B, then B is a necessary condition for A. Right? I didn't just tell you this and that you had to believe me. I gave you definitions for sufficient conditions and necessary conditions, and then you've proved the statement. That's pretty cool. Okay, then I hope you have fun with the homework and proving other such statements. Thanks so much.